In this problem, an applied 25 Newton force pushes on a 5 kilogram block that's resting on a frictionless horizontal surface. The force is directed downward at an angle of 20 degrees with the horizontal. We're asked, what is the acceleration of this block? So as is typical in a problem like this, I want to draw a free body diagram. Okay, so I still want to preserve the same angle of the force and the same length. I'm going to call this FP for push, and it is 25 newtons. Now I'll draw the weight of the block. The weight will be directed downward, and it's going to be 5 times 9.8, so it's going to be 49 newtons. According to the weight formula. Okay, there's also going to be a normal force acting on this block, but I don't really know how large the normal force is going to be. Now, if that force of push hadn't been there, then we know that the normal force would equal the weight. But with that push there, things are a little different. So I'm not going to draw the normal force yet. Instead, what I'll do is I'll break down the force of push into its components. Now, why am I doing that? Because it's at a weird angle. It's not an angle that's aligned with the x or y horizontal or vertical dimensions. So let's go ahead and find its components. All right, this will be FPX, and this can be FPY. Let's calculate what FPX and FPY are. This time, I'm going to use the full vector form of the components. And the way that works is we do the magnitude of the push times cosine of the angle of the push for the x component. And we would do the magnitude of the push times the sine of the angle for the y component. And if I want to put them into vector form here so that the left side matches the right side, we need to put an I on this one and a J on that one. Now what angle should I use? Should I use the 20 degrees for the push? The answer to that is no. What we would want to do is we've got our x-axis here, and this is our y-axis. And we want to find the angle as an angle that's measured counterclockwise from the positive x direction. So that is actually going to be our standard position angle for the force of push. How large of an angle is it? Well, we see that we've got a reference angle here of 20 degrees. That's the same angle that we had seen here. The reason why they'd be the same is they're what are called vertical angles in geometry. So if you put a straight line through the origin and you got a 20-degree angle here, then the angle that's opposite that would also be 20 degrees. All right, so what's our real standard position angle then? it's going to be 360 minus 20. It'll be 340 degrees for the push. So now let's go ahead and fill those in. We got 25 newtons cosine 340 in the I direction. It's 23.5 newtons. And let's find FPY as well. Negative 8.6. All right, great. So we can fill those in now. Okay, so we know that as this block is pushed, it is going to accelerate in the positive x direction. There's a little motion map of it. It's going to start off at rest. And then as time goes on, it's going to be accelerating to the right. Notice that it doesn't accelerate into the floor, and it doesn't accelerate into the sky either. That tells us that the forces are actually going to be balanced in the y dimension. And so when we see this force in the negative direction, and this blue force here, the weight in the negative j direction, those two forces have to be balanced by the normal force. So whereas the normal force would have been 49 newtons if nobody was pushing on the box, now because someone is pushing on the box, we need to have a larger normal force. All right, that's the complete vector diagram here. And we want to see which force out of all the possibilities is the unbalanced force. So it turns out that Fpx is the unbalanced force. So it is the thing we would use to calculate the acceleration of this block. We can use Newton's second law for that, where Fpx represents the unbalanced force, and m is the mass of the block. So we'll have 23.5 newtons divided by 5 kilograms. The acceleration is 4.7 meters per second squared. Now, what would be the normal force on the block? We'd have to start with the idea that the sum of the forces in the y direction is 0. And now let's sum them up. We have Fn plus Fg plus Fpy. Those are the three forces that act in the y dimension. Now let's put numbers to them. We don't know what the normal force is, so we'll leave it as a variable. Fgy will be negative 49 newtons. negative because it's down. Fpy is negative 8.6 newtons. If we solve that equation, we get 57.6 newtons. And that is going to be our normal force. So because the person is pushing downward, the floor has to supply a larger force in order to stop that block from sinking into the floor itself. Question C says, if there were friction in this situation, then what friction force would be required to keep the box moving with constant velocity? Okay. We know that there's an unbalanced force, Fpx, that makes the box want to accelerate forward. In order to stop Fpx, we need an equal and opposite force opposing it. And that would be a force of friction. Now, of course, we would still have the weight of the object, and we would still have Fpy, and then we would have our normal force, but they don't really matter when it comes to the x dimension. So what friction force would be required to stop this block from accelerating? We would need the force of friction to be 23.5 newtons so that it would match the Fpx. And the friction would have to be in the negative x direction.